The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Let's do a 1-minute review and then move on to the Clausius-Clapeyron equation and see how far we can go on that. So reminding you then, what you learned last time about phase transitions is you drew a phase diagram in temperature pressure space here. And then you had a triple point somewhere, which was a unique point at the triple point temperature, triple point pressure. Then there was a gas-solid coexistence line, which kept on going ad infinitum, and then a gas-liquid coexistence line with a critical point. So that allow you to go around. If you wanted to go from liquid to gas, you could actually go around this critical point and never actually see a phase transition. Then there was a solid-liquid coexistence line, which usually has a negative slope, except for the two most important substances on Earth, which are water and silicon. Right? So for water and silicon, we have positive slope, H2O and silicon. This is why why there's life on Earth, right? Did you hear the story why there's life on Earth because of this? No. This is a secret of life. Without this, this is why we're here, because of this property. The reason why these slopes come from the, and so I'll tell you the secret of life. But first, let me remind you what the coexistence curve is. dp dt coexistence is delta S over delta V, or delta H over T delta V, and that's the Clapeyron equation. Right. Now, the slope of the curves, for instance, if I look at the solid-liquid line, delta S for solid-liquid, I look at it up here, is going to be S liquid minus S solid. And you know that's greater than 0 because the entropy in a liquid state is much bigger than it is in a solid state. If you have a crystal, the entropy is very small. Liquid state, much more disorder. You've got a positive sign here. Yes? Questions?
I thought the slope went backwards unless it's forwards.
So this is almost everything. It has this slope here, which is a negative slope, and water has a positive slope, right? Is that wrong? It's wrong. Let's go through the argument. All right, all right. Let's go through the argument. Okay. So then you have delta V, and delta V is V solid minus V liquid. This is per mole. Now, almost every substance has V solid less than V liquid. So this is negative, right? So almost every substance, you have delta S divided by delta V is negative, a negative slope. You're right. So I have it backwards. I do have it backwards. Okay. See, I was really trying to make it so that my drawing was right, which is why I inverted the solid and the liquid here. So I really wanted to be right, but I ended up being wrong. liquid is less than solid. Well, this is water. Why do I have it backwards in my notes? I've got to correct that. So, right, so this is most substances is positive. Okay, so let me, all right, let's just do it this way. Okay. Most substances, okay, except for water and silicon. Because for water and silicon, this is reversed. Because the molar volume of solid for water is bigger than that for liquid, so this is bigger than 0. Thank you. Okay. Thanks for catching it. Okay, so what happens if the molar volume for the liquid is bigger than the molar volume for the solid? The density of water, which is the inverse of the molar volume, so the molar density is equal to 1 over the molar volume. So you've got the molar density for liquid is then smaller than the molar density for the solid. It's 1 over, right? So density, that's why ice floats, because it's less dense than liquid water. So what do you think would happen in the winter if ice didn't float in the Charles River? It would go to the bottom, it would freeze solid, and you would have no fish, right? You would have no life, it would freeze solid, and that would be the end of life. And 500 million years ago, there would be no fish, there would be no dinosaurs, there would be no anything, there would be no humans. That's the secret of life. And the fact that this is also the case is very useful for making silicon. Silicon for processing silicon. Another secret of life. Where would we be without silicon? Our civilization we'd still be, using stones and things, right? Okay, so it's super, super important. All right, so this is the Clapeyron story, which we ended up getting right, even though I insisted on getting it wrong. So what happens now is Mr. Clausius came around, and he realized that you can make some approximations that are very useful. So the first approximation is you can realize that the molar volume of the gas is always much bigger than the volume of the solid or the liquid. Okay? And so as a result, whenever you have these delta V's for sublimation, or delta V for vaporization, which is the volume of the gas minus the volume of the solid, or the volume of the gas minus the volume of the liquid, you might as well ignore the volume of the liquid or of the solid, and this can just be equal to roughly the volume of the gas. So this is the first approximation he made. So now if you go back to the Clapeyron equation up here, with this approximation, then dp dt at the coexistence line is delta H divided by T V gas for sublimation or vaporization. Right? You don't have the delta V down there anymore. Then the next thing that, next assumption that he realized you could make was, well, all these gases they're just like ideal gases. So we can, instead of having the volume of the gas here, we can use the ideal gas law. This is all, let's do all this per mole. So V is equal to RT over P. You can plug this back in here. And then you end up with the Clausius-Clapeyron equation. So this is approximation now. We put in RT over P for here. We have P delta H, where this is either sublimation or vaporization, divided by R T squared. So dP dt, sublimation or vaporization. And this is the Clausius-Clapeyron equation. two important approximations that go in here. And it's not valid for solid to liquid. Just you have to have a gas in there because of the ideal gas approximation that goes in here. OK, and once you have that, you can integrate both sides. You've got to put the temperatures on one side, put the pressures on the other side. Let me go ahead and cover this up here. So you have 1 over p dp dt is equal to delta H over RT squared. 1 over p dp dt, that's just like d log p. And that's another form that you're going to see often for the Clausius-Clapeyron approximation is d log p dt is equal to delta H over RT squared. And I'm freely dropping the sublimation and the vaporization because we know that's what I mean here. It's only valid for those two lines. So that's another form that you'll see. And that's not dt here. That's d log p dp. Yeah, that's right, d log p dt. And so now you can take the dt to the other side and integrate from point 1 to point 2. D log p is from point 1 to point 2 delta H over R t squared dt. And you make the usual approximation, which we've made before, that delta H is roughly independent of temperature, or very slowly changing with temperature. And that's fine as long as you're in a narrow temperature range, which is usually the case when you have these Clausius-Clapeyron equation problems. So you can take the delta H out of the integral, the R out of the integral, and you can integrate both sides to give you log P2 minus log P1 is delta H times R, divided by R, delta H divided by R, delta H over R times T2 minus T1 over T1, T2. It looks a lot like the temperature dependence of the equilibrium constant, right? And in fact, but it's not, right? And some people use that equation here instead of the equilibrium constant temperature dependence. That can give rise to problems because obviously they're not the same equation. But roughly has the same form. So another way that you'll also find this written is very often P1 and T1 will be some reference pressures and temperature, maybe 1 bar, let's say. T1, 298 degrees Kelvin. That's your reference point, and you want to find out the pressure temperature dependence in an equation. So if you rearrange your equations, so P1, T1 are now some reference point. They become numbers. So you have log of a reference point. T1 here is a number. So you often see this equation rewritten then as log P is equal to delta H over RT. And I feel like I've got a minus sign missing somewhere here. When you integrate this, the 1 over t squared, there's a minus sign. Oh, I took care of that by doing T2 minus T1 here. I think there's still a minus sign problem somewhere. I think there's a minus sign problem. Let me check the notes here. Minus 1 over T1 minus T2 over T1, T2. Where's my minus sign? T2 minus T1. Okay, so I got minus T1 minus T2 over T1, T2, T2 minus T1, H over 2, log P, delta H. Oh, no, okay, this is fine. All right, there's no minus sign problem. Plus a constant. Okay, so you'll often see it written like that. And that gives you a relationship between the pressure and the temperature then for a substance, where all the reference point information is contained in this constant C, which is where the T1s and the P's come from. Okay, any questions? We'll do a little example here of how this could be used. Okay, so let's switch to an example now. Let's go to the example. Let's first do the example which is at the very end of the notes. Here. Okay. So this is an example of RDX. RDX is a famous explosive, as I'm sure you know. And it's plastic explosive. It's got a melting point of 204 degrees Celsius, 481 degrees Kelvin. And it's a problem for, it's a very powerful explosive, and you can't see it in X-rays. So it's a problem at airports. You've got to be able to find if somebody's carrying a little piece of RDX in their luggage. And so the question becomes, what do you need to know to detect it? You want to find the vapor pressure. You're going to have a machine which basically is sensitive enough to detect molecules of RDX that are in vapor at room temperature. So the way that you do that is you do an experiment where you measure the pressure, the vapor pressure, as a function of temperature. And room temperature, it turns out that it's not volatile at all. The vapor pressure is really tiny. And so in order to get accurate numbers, you actually do your measurements at significantly higher temperatures than room temperature. You do it close to the melting point, so you're actually looking at the sublimation of RDX. You do it, let's say, at 400 degrees Kelvin, where the melting point is to 481 degrees Kelvin, right? So slightly below the melting point, you're looking at sublimation. And you plot log P versus 1 over T. And according to Clausius-Clapeyron, that should give you a straight line. And in fact, that's exactly what you see when you take RDX and do that experiment. You end up with a bunch of data points that fall nicely on a straight line, right? And then you can extrapolate to room temperature, somewhere here, let's say, 300 degrees Kelvin, and find out what log P is at 300 degrees Kelvin. And what you find is that, and that's the graph that's on the last page of the lecture notes, that the vapor pressure of RDX at room temperature is 10 to the minus 11 bar. That's 10 parts per trillion. So it tells you that if you want to detect RDX with a sniffer machine at the airport, that machine better be able to tell you, find one molecule of RDX out of a tenth of a trillion other molecules, basically, which is a really hard thing to do. Right. So this gives you a design rule for these pieces of equipment and why they're so expensive. Okay. Before we do the next example, let's see if any questions on Clausius-Clapeyron. Yeah.
Do you ever see that expression related as the exponential, or is it generally written and will be seen as the natural log of the pressure?
So P as some exponential here? You know, I don't recall seeing it as an exponential form, but that doesn't mean it's not used in the exponential form. This is an easy way to do it because then you've got a linear relationship, and generally we like to see straight lines, and so this gives you a nice straight line. Okay, so now let's do a slightly more complicated example, which is. So most of the time, you don't have pure material. You have a mixture of some sort. For instance, if I have a glass of water on the table at room temperature, above the glass of water, I have air. There's my H2O here. And then I've got some air, above the glass of water. And the air is inert to the water. It's not reacting with the water. So it's like an inert gas sitting on top of the water. Then I want to ask the question, what is the vapor pressure of the water in the presence of this inert gas, the air? It's not really the same as the problem that we've been looking at up here, right? Because this gas-liquid coexistence line, this diagram and this Clapeyron equation is all done for a pure substance. And at room temperature, we're sitting squarely in the liquid phase. We're not in the coexistence line at room temperature and 1 bar pressure. So if instead of having this system here, I looked at the system where I had the water, the H2O, with nothing on top, no air on top, except a cylinder. Now I better make the surface of my water a straight line, otherwise I'm going to get in trouble. There's the water sitting right here. And I put a cylinder with 1 bar pressure on top. My cylinder is going to sit squarely on the top of the surface of the water. Right? Because there's not going to be any water vapor at all at 1 bar pressure on that cylinder. At 1 bar, we're way up in the liquid phase. Right? I would have to decrease the pressure on that cylinder down to, I don't know, whatever the water vapor pressure is at room temperature here on this coexistence curve, 0.1 bar or something, 0.05 bar, something pretty small. So that's what we've been working on, this pure system. And now we're going to be working on this system here where we have air. There's a cylinder on top, 1 bar. And we want to know what is the vapor pressure of H2O in this system here. Is it 0? Anybody want to guess? If it's 0? No. We know there's vapor pressure there, right? And a good guess is that that vapor pressure here, it's pretty close to the pressure that you would guess by using this diagram with a pure water. But the key word is it's pretty close. It's not exactly the same. Right. So let me ask you this without looking at the notes now. Is pH2O in this problem here greater than, less than, or the same as pH2O in the pure Clapeyron case? Right? How many people think that it's the same? How about smaller than? Smaller than. Okay. A few people think that it's smaller than. How about greater than? Again, a bunch of people don't know what to answer. Okay. I think that if you think about it, what the difference is between here and there, you could probably reason which way it should go, which way the partial pressure of the water should go under 1 bar pressure room temperature compared to what you might expect it to be at room temperature with the diagram. So I'm going to give you a little bit of time just to think about it, without looking at the notes, what you think the right sign is here. Then we'll do the problem, and then we'll figure out where, if you were right or wrong. Okay. Okay. How many people say it's greater than? 1. 2. 2 brave people here. 2. All right. How many people say it's smaller than? Okay. Smaller than. So that I'm going to say large number. Okay. Many. How many people think it's equal? 1 person thinks it's equal. All right. Good. All right. Let's do it out now and see how it comes out, and then we can reason why it came out the way it came out, logically without actually doing math, because there's a way to reason it out that you should be able to do. Okay, so this is what we have here then. The system is we have this container. Let me redo it instead of writing air. So we have the liquid state here, some substance, and it doesn't have to be water. It's a liquid at some pressure P. And I'm going to say P capital. That's going to be the total pressure. And the total pressure is given by the piston here, P total, PT. And on top here, I'm going to have 2 substances. I'm going to have A in the gas phase. That's the water vapor. Some partial pressure P sub A, temperature T. And then I'm going to have the inert gas with some partial pressure P inert, such that the sum of the partial pressure of the inert gas plus the partial pressure of A is the total pressure, 1 bar in our case, with the water with the air on top. And the question, let me make a few more definitions. Okay, we're going to define P naught as the vapor pressure of pure vapor pressure of pure A. Okay, so that's what you would read off the diagram here. Okay, and what we want, the question we ask is, what is the partial pressure of A as a function of the total pressure? Right? That's what we're asking. As I'm increasing the total pressure, meaning I'm putting more and more inert gas in there, which way is this going? Is it going up, down, or staying the same? And we've got a bunch of votes up here. Most people think that it's going to go down as I put more gas in there. Okay, I know that if P, capital P, is equal to PA, then PA is equal to P naught, right? There's no inert gas. So that's the one extreme case here. If there's no inert gas, then the partial pressure is going to be what you read off that graph here. All right, so another way of saying what is Pi as a function of capital P is to ask the question, what is the slope? I've got 1 point here. If I can integrate the slope, then I have this equation here, right? So the other way to ask the question is, what is dPA dP at a constant temperature, where I'm keeping the temperature constant? And that turns out to be easier to calculate. These slopes are always easier to calculate than the absolute things. Okay. So we're doing an equilibrium here. We have an equilibrium between the liquid state and the gas phase, and we want to know something about this equilibrium as we change a parameter. Equilibrium, what do we always start with when we have an equilibrium problem? What's the first thing we think about? We think about chemical potential. Chemical potentials of A in the gas phase has to be the same as the chemical potential of A in the liquid phase. Well, I can't think of anything else to start with, so let me start with that. All right, so let's start by writing the chemical potentials being equal to each other, because we know that's true. So mu A in the gas phase, temperature, and with a partial pressure P sub A, is equal to mu A in the liquid phase, where the pressure on the liquid is capital P. What else do we know? Well, what else are we going to need? Well, before we do that, what we're after is the derivative. Let's take the derivative of both sides. We're looking at the derivative with respect to pressure here. Let's take the derivative of both sides with pressure and see what happens. So that let's take the derivative of this with respect to total pressure. Well, this isn't total pressure. This is the partial pressure of A. But it's a function of the total pressure, right? It's a function of the total pressure. Partial pressure of A is total pressure minus P inert. So we have to use the chain rule. So on this side here, we have d mu A dPA. So I'm taking d dP of both sides, right? D mu A dPA, and then by chain rule dPA dP, constant temperature, and then on the right-hand side I have d mu A dP, constant temperature. Okay. Well, d mu dP, that may or may not seem familiar to you. I never remember these things, but I always remember that these relationships are interesting, especially when you're talking about something like the chemical potential, which is really nothing but the Gibbs free energy. With respect to pressure, when we know that the variables that we use for Gibbs free energy are pressure and temperature, right? So this is the variable that goes with Gibbs free energy. So this means that taking the derivative of the Gibbs free energy with respect to one of its variables is something that we should know. So we go back to writing what the Gibbs free energy is. So dG is equal to V dP minus S dt. This is the fundamental equation for Gibbs free energy. And this is the Gibbs free energy per mole. So that's just the chemical potential, right? Same thing, right? And this is the derivative with respect to pressure, and this is the derivative with respect to temperature. So this thing here is d mu dP under constant temperature. It's just the volume. So now we have this equation where we started out with the chemical potentials, and we've got these d mu A dPA, we've got d mu A dP here. That's just the molar volume of the gas, right? Because this is mu of the gas phase here. So this is the molar volume of the gas. Then I have dPA dP. And this is very nice, because this is actually what I'm trying to get. I'm trying to see how the partial pressure of A changes with the total pressure. That's what I'm trying to calculate here. I know what this is. This is just an experimental number, right? And then on this side here, I have d mu A dP. This is the liquid phase. Derivative with respect to total pressure, that's the molar volume of the liquid. Right. V liquid. Great, I'm done. dPA dP total, constant pressure, is the ratio of the molar volume of the liquid of A divided by the molar volume of the gas. What's the sign? Volumes are positive, right? This has to be positive. There's no choice. It can't even be 0. It has to be positive, right? So that means the slope is a positive slope. As I increase the total pressure, P is going to go up. Yeah, if I integrate now this, starting till the total pressure is equal to PA, I'm going to get a curve that looks like this. Okay, if I write on this axis P inert, so when P inert is equal to 0, total pressure is PA, I'm going to start at P naught, and I'm going to go up from there, positive slope. So, who was right? Right, a couple people are right. So let's think about it in a different way. Okay, let's think about it in a different way. So we did the math, and we found that actually and it turns out to be a very small amount. Okay? You do a very good job by just taking this curve here and using the pure substance. In fact, in the notes, we have an example of how much it changes for mercury. So for mercury, at 100 degrees C, for pure mercury, the vapor pressure is 0.27 bar. If you add enough inert gas to make it 1 bar for the total pressure, you go from 0.27 to 0.2701. Not much of a change. So you do a really good job just picking this. And if you go to 100 bar, then you increase it to 0.28. So it takes a lot of pressure on top, a lot of extra inert gas to really make much of a difference. But let's think about why it would make a difference just logically. So in the absence of this inert gas here, I just have the pure substance. I add some inert gas. What happens to the entropy on top? It's increasing, right? Do systems like to have more entropy? Yeah, right. So I have a lot of inert gas here, a small amount of A. What if I had a little bit more A in the presence of the inert gas? Which way would the entropy go? It would go up a little bit more, get even more disorder. Right? If I have nothing, if I have no A here, up here, and just the inert gas, then there's no entropy of mixing. I had a little bit of inert gas, there's a little bit more entropy of mixing. Right? Eventually, I had more and more, entropy of mixing goes up and up and up, and eventually it comes back down to where I have pure A on top. So the entropy of mixing up here is driving the increase in the pressure in the partial pressure of A. Entropy is this amazingly important term. That's what we saw. Entropy of mixing was responsible for equilibrium, right? Without entropy of mixing, then everything would go directly to the products. You'd never have an equilibrium, another secret of life. So entropy of mixing here is driving this positive slope. That's another way of thinking about it. And that's why you can guess ahead of time what the signs of these things ought to be without doing the math. All right, any questions? OK, so there's another sample problem in the notes, which is a sort of like a standard problem where you're given a Clausius-Clapeyron equation for the substance in this form. So if you look at it, log P is minus some energy divided by RT plus some number. Okay? And in this case, it's negative. The delta H is negative for the substance that you have there. And you're given it for the liquid phase, for the vapor pressure above the liquid and the vapor pressure above the solid. You can, because the only way it doesn't work is if you're looking at solid liquid. So, and then you're asked to manipulate this equation to find different properties. For instance, the triple point. It's a very common thing to get the triple point from this. The delta H, it's a way to get delta H. Just like we saw for the RDX, right? The data points formed a straight line, and the slope gave you delta H for RDX, delta H or sublimation for RDX. Right? So this is the way that this equation is used for problems. I'm not going to do this problem. Instead, I'm going to go ahead and forge ahead to the next topic and start it. This is the topic we're going to do after spring break. And it really is a topic that follows this pretty straightforwardly. Well, it's more complicated, but it's similar to this problem here. So we saw that in real life, yes, question?
How far in the lecture is the exam on what exactly vacation going to?
The exam, or there's an exam, which is, oh, I forgot about the exam. Right. So let's see, there's a problem set that's due today, right? The exam will be up to the problem set that's due today, which means that what I talked about today is not going to be on the exam because it's not covered in the problem set. OK? So let's say it goes up to Wednesday's lecture, which means you might still have a phase transition problem, right? In fact, you're very likely to get a phase transition problem. It's very likely to be the case, because it's an easy problem to put together. But you don't have to worry about Clausius-Clapeyron. You do have to worry about Clapeyron, but not Clausius-Clapeyron. Okay. So for the exam, we're going to put on the web last year's exam, and you guys are going to do reviews, the usual thing. Yeah?
Is there any way you can put a blank and the answers but separate?
So that you don't see the answers? Yeah, absolutely. This can easily be done. We'll do that. Any other questions about the exam? Now, I don't remember. Is there a problem set that, so I'm not assigning a problem set today, right then? Right, OK, good. Right. Because I hadn't loaded it up yet, and so now I won't load it up. OK. Anything else? OK, so let me tell you where we're going to go then after the break. So after the break, we're going to be starting to talk about things that are called colligative properties. Colligative properties are the properties like the vapor pressure lowering when you have a mixture in a liquid. Instead of having a pure substance, you have a mixture of substances here. And then the vapor pressure of those substances above gets lowered. Anybody want to guess why they get lowered? What's the magic word? Entropy of mixing, right. There's more entropy of mixing if you've got a mixture in the liquid than if you have a pure gas up there. So usually, let me back up. Usually it's when you have a solute like salt and water, where water is volatile and the salt is not, right? A salt and water solution will have a lower vapor pressure than a solution of pure water because of the entropy of mixing in a salt and water solution. The salt and water solution, we have a lower melting point, and that's significantly lower, which is why we use it on roads, right? That's a colligative property. Osmotic pressure, which you've already sort of heard about, why saltwater fish are unhappy in fresh water. That's a colligative property. So we're going to go through these colligative properties, and the mainstay of these colligative properties is that we're going to be talking about mixtures in the liquid phase. Here we talked about a mixture in the gas phase, changing some property. From now on, we're going to be talking about mixtures in the liquid phase, pretty much. And so our goal is going to be to predict the way that that properties change as you have these mixtures. Okay, so the standard mixture that we're going to have is to have a binary liquid-gas mixture. So that means we're going to have two substances, A and B. And at first, we're going to make it as general as possible. So we're going to have liquid phase of A, a liquid phase of B. So for instance, this could be vodka, right? Water and ethanol. And water and ethanol are both volatile. So we're going to have water and ethanol in the gas phase. Okay? It's a mixture. They're perfectly miscible in the liquid phase, A and B. And there's going to be some fraction, molar fraction of these things. We're going to have a molar fraction in the liquid phase for A and B, and some molar fraction in the gas phase for A and B. I'm going to call it YA and YB. That's the molar fraction in the gas phase. And there's no reason why the molar fractions in the gas phase should be the same as that in the liquid phase. And we know that. We know that ethanol is more volatile than water. And so if you have a glass of vodka, then you can smell the alcohol because it's coming out, right? And, but the vapor pressure is very slow, very small. It's the usual. It's pretty close to the usual vapor pressure. And our question is what we're going to be asking is how many, if I give you the total pressure and the temperature here, what else do I need to know to find out all these molar fractions? Okay. So let's first see what all the variables are that we have. Usually we have two variables, the temperature and pressure, and that's enough to tell us everything. Right? But here now we have a mixture, so we're going to need more than that. We're going to need 4 variables. We're going to need the temperature, the pressure, and we're going to need the molar fraction of A in the liquid phase and the molar fraction of A in the gas phase. We're not going to need any more than that. Actually, we're going to need less than that. But those are the 4 variables that we can easily identify here. And we don't need YB and XB because the sum of the molar fraction has to be equal to 1. Right? YB is 1 minus YA. XB is 1 minus XA. Right? So we don't need Y. So these are a priori the independent variables that we have to work with. Now, we have some constraints here. We have a constraint. Our constraint is that we are at a coexistent point. There's a coexistence between the gas phase and the liquid phase. And, and what does it mean for A, liquid, to be coexistent with A in the gas phase? Chemical potential. The chemical potential of a molecule of A in the liquid phase here is the same as the chemical potential of A in the gas phase. So we have two constraints. We have mu A for the liquid phase is equal to mu A for the gas phase, and mu B for the liquid phase is equal to mu B for the gas phase, right? So we have 4 variables, 2 constraints. That means that the total number of independent variables we have is just 2. It's the number of variables 4 minus the constraints. Okay? Or you could say 6 variables if you include YB and XB, and 4 constraints. Whatever way you count it, you just have 2 degrees of freedom. Okay? So we have 2 degrees of freedom, which means that if you know the temperature and pressure, then you still know everything at the coexistence point. You still know what the molar fraction is of your 2 substances in both phases. So that's really powerful. Or if you know just the molar fraction of A and the temperature, then you know the pressure above, and you know everything else. So in this very complicated mixture here, you still only need to know a couple things to tell you everything about this mixture. Okay, and this is this example here is a specific example of something called the Gibbs phase rule, which you've seen before in this diagram, diagram that we wrote here, where let me write down what the Gibbs phase rule is first. The Gibbs phase rule tells you the number of independent variables given a number of constraints. So it tells you that the number of degrees of freedom, the number of independent variables in a mixture, in a complicated system like this, is equal to C, which is the number of components. So in this case, it would be 2 components. You have A and B. The components is the number of independent species that you have, minus the number of phases. So here you have 2 phases, the gas phase and the water phase, plus 2. Okay? So for this example here, then we would have 2 components, C equals 2, 2 phases, liquid and gas, A and B are the components, and then plus 2. So 2 minus 2 plus 2, F equals to 2, 2 degrees of freedom, 2 independent variables. If I'm looking at this diagram here, in this diagram here I have C equals 1, 1 component. Right? If I'm sitting where there's only one phase, say the liquid phase or the gas phase, then P equals 1. Then F is 1 minus 1 plus 2 is equal to 2. 2 degrees of freedom. And so in the pure phase, I'm in a plane. The pressure and the temperature are my 2 degrees of freedom. I can freely move around the plane. Right? At a coexistence line, then the number of phases equals to 2. Then I have 1 minus 2 is minus 1, plus 2 is 1. The degrees of freedom is 1. That's a line. I have 1 degree of freedom. I can move a line in a line in the plane. Right? Then if I change to the triple point, where the number of phases is 3, then the number of degrees of freedom is 1 minus 3 is minus 2 plus 2 is 0. I don't have any degrees of freedom. I'm stuck at 1 point. So this is an example of the Gibbs phase rule, specific where C happens to be equal to 1. Then this is a more generalized example. Okay. So next time then, what we'll do is we'll start by deriving the Gibbs phrase rule, which is not so hard, and then start on our way to the colligative properties. And then you'll have an exam.